So we've talked about various ways to solve differential equations analytically. And we talked about first order differential equations. So we've talked about separable equations. We've talked about linear equations. We've talked about exact equations. And we've talked about various substitutions. And these are all analytic methods, okay? We analytically solve the differential equation and we end up getting either implicit or explicit solution, and it's exact. We're going to describe a numerical method now, and it's called Euler's method, okay? And so let's take a look at this differential equation here. Y prime is equal to 0.1 square root of y plus 0.4 x squared. And it's the initial value problem, so we have y of 2 equals 4. This cannot be solved in any of the analytic methods that we've described above. And it must be solved then numerically. Okay, numerically is basically using computation, using discrete steps to solve the differential equation. You don't get an exact solution that you write down, but you basically compute it. Okay, and going back to the qualitative description of solutions. For qualitative descriptions, we looked at the direction field. Okay, and suppose here's our direction field, right? Well, the solution curve is always tangent. So here in orange, you have an actual solution curve. But what if we decided to do this, right? We start at some point here, okay? And we say, well, look, we know that the solution has to have a slope this way. So why don't we just draw a line, okay, with that slope? And so we'll end up drawing this line here, okay? And how long will that line be? Well, it depends on the step size, how far we want to go along the x-axis for that one line. You could imagine that if we have a very large step size, all we're going to get is just the line, and it's not going to be accurate at all. So we decide on how far along the x-axis we want to move before we stop again and say, all right, well, now we're at this new point here. And at this new point, we have a slope there. And how do we get the slope, by the way? The slope is given by taking this point and plugging it in here. This has an x and it has a y. And we just plug the x and y in there and we get the slope. And so we calculate the slope and we say, okay, well, this next line, it's got this slope, and we're going to, move along h step to the right. And we draw another line. And then we get to this point. Okay, this is on the y-axis, so we'll put in x equals 0 over here, and y is some positive value, and we get a slope, and we say that the slope is a certain value there, and we draw a line again and move h units to the right, and we keep doing this. Okay, we stop here, we do the same exact thing, and we basically approximate the solution this way. Okay? This is called Euler's method in a nutshell. And the equation for a line, just using that y minus y naught equals mx minus x naught, where m is the slope, is this here. You could solve for y, and this is basically an equation of a line. All right, and so what we're going to do is basically get equations of lines for each of these, okay? Each of these segments we're going to get the equation for the line there, the lineal element. And this process of, instead of going from like an exact solution curve to just a line, that's called linearization, okay? We just basically approximate the solution curve as a line for a segment with step size h, okay? Translation h on the x-axis. dy dx is equal to fxy. And so instead of dy dx, we have this fx y in there, okay? And if we start at the point x naught, y naught, if this point over here is x naught, y naught, down here, then we would plug that in, right? We'll plug in y naught, x naught, and for the slope, we'll plug in x naught and y naught to the slope function to get the slope, and that will give us, for example, the first line. And then we're going to repeat this process and get the second line, and on and on. So here is Euler's method in a nutshell. For the initial value problem that we see here, we have this recursive formula, okay, where n is equal to 0, 1, 2, and h is called the step size. It's how far we move along the x-axis. The smaller the step size, the more accurate the results will be in general. So, but here's the algorithm, the recursive formula. Xn plus 1, so the next n is xn plus h. So here this is x1. So x2 is going to be x1 plus h. x3 is going to be x2 plus h. Or we could just write it as x naught plus nh. So you just start here and you add, like, say, 2 h's to get to x2, 3 h's to get to x3. Okay, that's that formula there. And what about y? Well, that we get that from the linearization. All right. Yn plus 1 is going to be the yn, so the previous y. So here, this, for example, y1, plus h. Where did that h come from? That's x minus x naught, okay? That's x minus x naught. So it's just one step there, and so you get the step size. And f, xn, yn is the previous slope, okay? So, you start at a point, you find the slope there, and you project that initial slope all the way through that whole line, okay? You could start here, you project that slope all through that line. You start here, you project that slope all through that line. Start at the green, you project that slope. Now, of course, the slope's changing along the green line, right? If we chose this point here, the slope might be up a little, but that's why it's an approximation. And so here's how you update yn plus this is how you get yn plus 1, the next y, okay? So let's look at an example. So consider this initial value problem. Use Euler's method to obtain an approximation of y 2.5 with step size h 0.25. So this is very algorithmic. You go through it by hand, maybe a few times, and you get the experience. And then, of course, you'll do it through computers, right? So you have dy dx is equal to f of x. So we identify with f of xy, the slope function, this. And we start at x equals 2, and we want to approximate y at x equals 2.5. And we're using step size 0.25. So what does that mean? Well, we got to hop twice, because 2 times 0.25 is 0.5, and 0.5 plus our initial point, which is 2, is 2.5, which is what we want to approximate. So we're going to do 2 steps. So, all right. You start the algorithm with the initial conditions, x naught equals 2 and y naught equals 4. Then to get x1, you have x naught plus h. So you get 2 plus the step size, and you get 2.25. y1 is y naught plus h times the slope function at x naught, y naught. Okay, so you plug in here the x naught. Okay, so you plug in what you have from the previous step, not this one, okay? Not x1. And so you plug those values in. How does this function look? We have a function fxy, so you just put y naught and x naught. and then you actually put values for them. So this is h, this is going to be y naught, okay, initial y, and this is also y naught, and x naught is 2. This is 4 times 0.4 times 2 squared, and you get 4.45. So what this step is telling us is at x equals 2.25, y is approximately 4.45. So we started at this x naught, okay, y naught, and now we got to x1, y1, okay? That's what that means. We're getting to x1, y1 up here. All right, well, that x is 2.25. We want to approximate y at 2.5. So we do another step. So x2 is equal to x1 plus h, or x naught plus 2h. And you get 2 plus 2 times 0.25, which is h. You get 2.5, okay? And y2 is y1 plus h, fx1, y1. And again, we plug in, for x1 and y1. Make sure this is x1, not x2, okay? Don't confuse x2 with x1. And plugging these in there, you get this value. And so y at 2.5 is approximately equal to y sub 2 that we see there. And you could imagine that with smaller step size would get even more accurate results. Here we don't have an exact value because we don't have an analytic solution. So we don't have much to compare it with. But nevertheless, let's go ahead and define ideas that will help us compare actual solutions to numerical approximations. So one is the absolute error, which gives you which is the absolute value of the actual value minus the approximation. You also have relative error, where you take the absolute error above and you just divide by the actual value. So you have the actual value minus the approximation over the actual value. And you also have something called percentage relative value, where you take the relative value and multiply it by 100, basically. So you'll have absolute error over actual value times 100, or just this relative error times 100. So let's look at another example, and one where we actually do have the exact solution, and so we can make comparisons. This y prime equal to 0.2xy with y1 equal to 1 initial value. And we want to use Euler's method to approximate y at 1.5 using step size h.25. So again, 2 step sizes. And we want to compare the absolute and relative value for approximations using h equals 0.25 and 0.1. Okay, similar to above, the same sort of algorithm that we have above. Again, n equals 2 steps because we want to jump from 1 to 1.5, going steps of 0.25. These are our initial conditions. This is the algorithm. At y1, which is at 1.25, you get 1.05, and then at 1.5 you get 1.11563. So y at 1.5 is approximately equal to this. Now we could actually get the exact value. Here's the exact solution. Okay, it's e to the 0.1 times x squared minus 1. How do we get that? Well, this equation is separable, so we could integrate. We've done a video on separable equations, so you could take a look at that. But using separable, using separation of variables, we could integrate and get this actual. So this is going to be the actual value. And here we have a table with the steps that were taken. The initial step here is 0, the xn, yn. The actual value is obtained by plugging this x n into the solution. Okay, you'll get the actual value there. And the approximation is this, 1.05. So to get the absolute error, you'll do the actual value minus the approximation. You get this. And of course, you take the absolute value according to our definition. but here it's just positive anyway. Now, relative error is you take the absolute error and you divide it by the actual value. Okay, and if you do that, you get this right here. And then you take the percent relative error, you multiply by 100, and you get 0.74%. Okay, so I write out explicitly how to get each of these values just for this row. The rest we could just state it. You know, it's similar. We would just plug, instead of 1.25, for example, we'd plug 1.5 to get the actual value. And the absolute error is going to be the actual value minus the approximation. Relative error, you divide the absolute error by the actual value, and you multiply by 100 the relative error to get the percent relative error. And so we're off by 1.5% with step size 0.25 once we get to for an approximation of y at 1.5. But what if we chose a smaller step size, 0.1? Okay, if we chose 0.1, we start at 1, we want to get to 1.5. Well, we got to take 5 steps, right? Because 5 times 0.1 is 0.5, and we want to go from 1 to 1.5. Doing the same thing above here, we'll get these values, okay? We don't go walk through this because, of course, it gets tiring. It takes a lot of time. But something to note here is the error is better than above, okay? The error for 1.5 is 1.546. The error here is 0.64. But something that you do notice, this is a general trend here, is that the error tends to increase the farther steps you go along. That makes sense because errors build on errors, right? You know, we start here, you know, we're already far from the solution curve. You know, this is the solution curve, for example. Already far from the solution curve, and then we keep going. You know, sometimes you'll accidentally come back to close to the solution curve, but I wouldn't count on that. In general, the trend is you'll just keep getting farther and farther from the solution curve, okay? Even though for solutions that, you know, change a lot and go up and down, you know, that might not be the case, but you can generally expect that your error keeps getting greater the farther steps because you're building approximation upon approximation, okay? And something to note here is that Euler's method is one of many numerical methods, and it's quite simple, so we start with it. There are more accurate methods, such as the Runge-Kutta method of higher order. You could basically see Euler's method as the Runge-Kutta method of order 1. Higher Runge-Kutta methods, they basically, you know, why take this slope here, the slope of our vector field here, and extrapolate it all the way down? Why not choose multiple slopes along a line, an average, for example? Why just take the initial slope and assume that, you know, the slope's constant all throughout there, which you could do, or, you know, assume that that's a fair approximation. What you could do instead is go through your whole step size and take samples of various slopes along the step size, and the more samples you take, the more accurate, and average these somehow, okay? And that's basically the basic idea of Runge-Kutta methods. So when we talk about numerical methods, of course, we'd like to compute. Doing these computations by hand is very tedious. And why should we when we have computers? So a free kind of software that you could use is Wolfram Alpha. Now, the proprietary kind of from this parent company, the proprietary software from Wolfram is called Mathematica. But sometimes you could put in Mathematica functions into Wolfram Alpha, and it actually, you know, just respects the Mathematica format. For example, here, plot 3D. So if you notice, this is 0.2xy, which was the slope function for the differential equation that we were looking at. And here we're plotting from x between 0 and 3 and y from 0 to 2. We gave this Wolfram alpha, this function, in the exact mathematical way. And we get a plot, okay? This is a 3D plot. And the z value, okay, the z value here is the slope, okay? So the z value there represents the magnitude of the slope. And here you could see the sort of level curves, okay, of this function. All right. We could also plot the direction field of the function, okay? So here's the differential, and we just write direction field, and even I intentionally spelled it wrong to show you that this language is pretty robust. It could kind of guess what you want. And so it'll plot the direction field for the differential equation that we see. It interprets and it'll plot the direction field. You could see these small vectors giving you the direction field. Now, there is a exact way to get Mathematica to plot the direction field, and it's called vector plot. I tried it here, and sort of ironically, despite Mathematica being made from this company, it just prefers that you give it the command in a natural language sense to just say direction field. But this is Mathematica, which is proprietary. You got to buy it. But if you do have it, you could put in this function, and it'll pretty much give you this. Okay. Also, Euler's method. So look how I asked Wolfram alpha to give me the results of Euler's method. I put Euler's method for the differential equation with the initial value with step size, and it interpreted all that. And notice that the numerical solution here is in blue, and in orange is the exact solution. And this gives you the various step sizes, okay, the various solutions, the various approximations, okay, and you could go down. So there goes 1.5 for us, and it'll actually give you the error as well, okay. All right, and so here you get various approximations using the step size above. And something to point out here, okay, it even gives you the exact solution there. We wrote it in a little bit of a different way. It shows you how good these various methods are for solving. And you can see the Euler method has a pretty large global error. And this Dorman-Prince method has really small error. Runge-Kutta methods, third order Runge-Kutta method, for example, has fairly small error, nothing compared to the other ones there. These are just numerical methods. And something to note here is the Mathematica input. Okay, so for a lot of these numerical programs, they don't have this sort of natural language interpretation, and so you would input the functions that you see there. And again, you could probably do this with Sage Math, which uses it's open source and uses more of a Python language. MATLAB, that's proprietary, but it also has ways to solve differential equations. And finally, we could even tell Wolfram alpha to do Runge-Kutta of order 4, okay, fourth order, for the same differential equation. And this here is the error, okay, this is the, look at that, the exact differential. You could barely see the difference between exact differential and a numerical solution because it's pretty good, okay? And so here you'll get step sizes using the Runge-Kutta method. And the Runge-Kutta method, again, just basically, instead of just taking the initial slope, does a weighted average of the different slopes in one step size. Okay, so you get more accurate results actually. And you could see here the very small error that you would get with just fourth order Runge-Kutta. That's aside from the other methods that we discussed or we saw, like the Dorman-Prince method. And finally, this is the Mathematica input that you would use. And, you know, there's, again, other functions depending on the software that you use.